Hey, so this is the first of a couple videos that we're going to do on different types of organic molecules, as well as the the reactions that those molecules can undergo. All right, so the first type of organic molecule that we're going to be talking about is alkanes. All right, so alkanes, they're the simplest type of organic molecules. What makes something an alkane is it's nothing but carbon single bonds or carbon hydrogen single bonds. All right, there are no double bonds in an alkane. All right, so one of the things that alkenes are most used for is fuel. All right, so if you've got gasoline that you put in your car, essentially take take a chain of carbons, make it about 8 carbons long, and it doesn't have to be a straight line. All right, it can be branched at different points. All right, that's octane. All right, that's the main component that's going to be in gasoline. All right, so why are alkanes so often used as fuels? All right, and that is because they are the most highly reduced form of organic molecules. All right, so what does that mean? Let's compare ethane, which is an alkane, to ethene, aka ethylene, which is an alkene, to acetylene, aka ethine. All right. So one thing that you'll notice about this, so when I did these, when you show these reactions here, notice the balanced reactions might be a little bit non-standard. Like you see 7/2 of an O2, and the purpose for doing that is so that you can show these so that it is always going to be per one molecule of the hydrocarbon. All right. So if you were to actually balance this the normal way, this would be 2 of this plus 7 of this plus 4 of this plus 6 of this. You just have to double everything. But because we do this, we can list the enthalpy of combustion of this per mole of this starting material here. And what you can see here is that when you compare the enthalpy of combustion, which is essentially just a measure of how much heat is given off when you burn these things, all right, you can see that there's going to be more heat given off when you burn an alkane versus the alkene or the alkyne that directly corresponds to the alkane. All right, so molecule for molecule, an alkane will give off more energy when it's combusted than an alkene or an alkyne. Okay, and I just want to quickly go back to that definition. Why do we call this the most reduced? All right, so remember one of the definitions of a reduction is going to be the addition of hydrogens. All right, so if you start here, what's the difference in going from here to here? We're adding hydrogens. All right, so that meets that definition of a reduction. All right, and again, going from here to here, that is also addition of hydrogens. All right, so one thing that you'll notice and you'll see this in biochemistry, the more reduced a compound is, the more energy it possibly has. And one little bit of evidence of that is if you ask yourself, what's the most oxidized form of carbon? All right, well, the most oxidized form is carbon dioxide. All right, does carbon dioxide have any use as fuel? No. In fact, if you put it on a fire, it puts it out. All right, so reduced things have lots of energy. Oxidized things don't tend to have lots of energy. So one thing hopefully you know a little bit about is where do we get our alkanes from? All right. So well, if I just said that gasoline was just a mixture of alkanes, that should give you a hint. It comes from crude oil. All right. So how do we separate this? All right. So what I'm showing down here is an example of what's called fractional distillation. All right, and this is what's going to happen in just about any oil refinery. Okay, so whenever you have crude oil, you're going to have a mixture of different alkanes. All right, anywhere from methane, which is a 1-carbon alkane, to ethane, which is 2 carbons, all the way up to things that have 20 to 30 to 40 carbons in the chain length. All right, and so you start off with that mixture. All right, and so what you're going to do is you're going to heat that, and picture this as being a big column right here. All right, And so what happens is that as you heat this, eventually the materials in this are going to start to boil. All right, so when it boils, the gas, the vapor, is going to start to rise through the column. All right, well, ask yourself this. What's going to be able to go higher? Things with higher melting points, higher boiling points or lower boiling points? All right, well, the things that are most likely to stay in their gas form are things with very low boiling points. All right, so for example, the boiling point of hexane is 68.7. All right, the boiling point of octane is 125.7. All right, so if we just use boiling water as our heat source, hopefully it makes sense that hexane would be able to rise up the column because it would be in its gas form at that temperature, whereas octane would still be sitting down here as a liquid. All right, and something in between would also boil. All right, so essentially what's going to happen is that the alkanes with the lower boiling points, all right, and that's going to be the ones that have the shorter chain length, are going to rise farther up this column, all right, because they can stay in their gas form at temperatures where the higher boiling alkanes are going to become a liquid. And what's going to happen is when things turn into a liquid, the drops of the liquid can collect here, and they're eventually going to drop, just kind of drain down into a tube, and they can be collected. All right, so this would be a collection of a higher boiling fraction of your crude oil. All right, things that have intermediate chain lengths, well, things that were liquid here, remember that's still going to be a hot liquid. And that hot liquid, if it were to contain some of these smaller chain length, well, that would cause those to turn into, to stay in their vapor form, and they would continue to go up the column until they would turn into a liquid here and drain down. All right, but again, right here at this point in this column, that's going to be a hot liquid, and it's going to be hot enough that the even lower chain length things are going to want to continue to exist as a vapor, and they're going to go up higher up into the column, and eventually they're going to turn into a liquid and drain down this way. All right, so essentially what's going to happen is that if you think about the things that are lower are going to be the hottest. All right, the hottest temperature is going to be up here. All right, the things that will liquefy at the hotter temperatures will drain off. All right, but the things that can stay vapor at that temperature are going to continue to rise. All right, so so this is the basic process for fractional distillation. All right, and if you've ever looked at a picture of an oil refinery, one thing that you'll notice is you've got a lot of these really tall columns. All right, and essentially that's what you're doing just on a very, very large scale. All right, so you're going to be heating these things at the bottom, and those vapors are going to be rising up these columns. All right, and again, the lower boiling fractions are going to go up higher. The higher boiling point fractions aren't going to be able to make it as high, and that's the way that they essentially are going to make things like jet fuel versus gasoline versus kerosene, because these things just have different boiling points. Okay, so one thing that you're going to definitely be expected to know is this general trend that as you add carbons to the length of to the chain length of the alkane, you're going to get an increase in both the melting point and to the boiling point. All right. Eventually, if you get add enough carbons in the chain, you eventually get to a wax, and that's going to be something that would actually be a solid at room temperature. All right, but you notice in both cases things get higher as the chain length gets larger. All right, so just as an example of how this is played out, I'm just going to give the example of rubber cement. Okay, if you look on the side of rubber cement, you'll notice that it contains heptane. All right, and all heptane is if you put 7 carbons in a chain. All right, and they're all carbon single bonds, carbon hydrogen single bonds. All right, so why did they choose heptane? All right, why not hexane, which would be 1 carbon shorter, or octane, which would be 1 carbon longer? All right, well, let's think about hexane. All right, it's got a boiling point of 68.7 degrees. All right, well, one of the problems with doing that is if you think about it, every time you were to open the top of the rubber cement container, some of that hexane is going to evaporate. And if you keep on doing that enough, essentially you're going to notice it's going to be the same thing that happens if you were to leave the top off of a regular bottle of rubber cement for long enough. All right, the solvent evaporates and it just becomes this big hunk of latex. All right, so same thing would happen if you used hexane. It's just it would happen a lot faster. All right, because it would evaporate. The stuff would evaporate away so much easier because it's got a lower boiling point. All right. Another thing about it is that if you were to actually use it, it would dry so incredibly quickly. If you think about the way rubber cement works, you can put it down on a piece of paper and you can still move the piece of paper over top. It doesn't set right away. All right. And you actually want it to be take a little bit of time. All right. If you used hexane, put it down, you wouldn't have that property because it would evaporate so quickly that it would set before it would let you move things around. All right. Well, what about octane? All right. So the problem with octane is it boils at 125.7. All right. So it would be slower to evaporate than even water. All right. So if you think about rubber cement, you want things to be able to move around for a few seconds, but after a while, you eventually want that solvent to evaporate, leaving nothing but the pure latex. All right. And if you did that with octane, it would, instead of your thing setting in a matter of minutes, it would take hours, if not days, for that material to finally set, because that's how long it would take this stuff to evaporate. So the next part actually has to do with a problem of economics. All right. So when we have crude oil, we just get it exactly how it comes out of the ground. All right. It has whatever alkanes are in it. All right. So we talked about the fact that you can use this fractional distillation to separate these by their different carbon chain lengths. And by the way, this is a little bit oversimplified. You would definitely be able to separate a C5 something versus a C6 something versus a C7 something. It's just I didn't want to draw a column here for every single carbon length. All right. So the problem is that there is much more usefulness in the lower chain length alkanes. All right. This is where your gasoline and a lot of your solvents are going to come from. There are some use, like here, like paraffin wax that you might use for cooking. We might get from these, and eventually the stuff that really doesn't like to boil at all. If you've ever seen people paving roads, where they've got that hot tar that's mixed with a bunch of rocks, all right, that's asphalt, all right, that hot tar is basically going to be those really high chain length alkanes that are just a leftover byproduct when you're doing this distillation, and you can use that to pave roads. Okay, so the problem is that there's just way more demand for the stuff that's this chain length than there is this. All right, so the question is, what are we going to do with all this leftover high carbon length, chain length alkanes? All right, well, the thing is, there's this process that allows you to turn some of the higher chain length alkanes into smaller chain length alkanes, and that process is called cracking. All right, so essentially, there's a couple ways to do it, but the modern way of doing it uses a catalyst called a zeolite, and you heat it. And when I say heat it, you've got to heat it pretty high. All right, probably 300 to 400 degrees Celsius. All right, which interestingly enough is cooler compared to how high you'd have to get it if you didn't have the catalyst. All right, but anyways, what happens when you crack an alkane? You always get two products. You always get a shorter length alkane plus an alkene. All right. So if you count this, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons there. And if we count these total, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So the combination of these two molecules adds up to 10. All right. And if you counted up all the hydrogens on both of these, you'd notice it's the same amount as you had here. All right. The thing about cracking is it doesn't just necessarily make one set of products. It could have cracked at a different position, and that would have created this alkene and this alkane. All right. So during the process of cracking, you're going to end up creating a much smaller length alkanes, and those can be repurified to to give you more of the types of alkanes that we find more valuable.